This video is about the relationship between pressure and temperature. We're going to be using a gas law that we're going to learn about this week. That gas law is called Gay-Lussac's law. Here's his picture here. Back in the early 1800s, he studied the relationship between temperature and pressure. He found that gas pressure and Kelvin temperature are directly proportional at constant volume. For example, if the absolute temperature, that's temperature expressed in Kelvin, not Celsius, is doubled, the pressure is doubled. If the pressure is cut in half, the absolute temperature is also cut in half. Those are just examples. If the temperature was tripled, the pressure would be tripled, and so forth. What that means is when gas volume is held constant, constant means does not change, the following equation expresses the pressure and temperature relationship. P1 stands for pressure 1, T1 stands for temperature 1, P2 stands for pressure 2, T2 stands for temperature 2. If any three of the variables in this equation are known, then the unknown fourth variable can be calculated using simple algebra. This diagram right here shows you how you could manipulate the equation in different ways. And this picture right here shows how an increase in temperature, so this one has a higher temperature, leads to increased pressure due to more frequent and forceful collisions with the side of the container. So here's our first example. We are given the values for 3 of our variables, and we're looking for the missing one. So what we're going to do is go ahead and plug in our numbers and solve for what's missing using algebra. First, we want to check to make sure our temperature values are in Kelvin. So Kelvin is a key here. We must use Kelvin, and we have them, so we're okay. Okay. But if we did have Celsius, we would have to convert from Celsius to Kelvin. So we're going to write down our values that were given in this proportion setup. So 100 milligrams of mercury, that's pressure, 1, over 50 Kelvin. And then we are given T2, that's 100 K. But we do not know P2, so you could fill in P2 right here, or you could use an X or whatever variable you want. Now we need to solve. You could cross multiply and divide to solve. You can also just identify the relationship or the factor that multiplies the two, basically 50, to get you from 50 to 100. So we want to know 50 times what equals 100? Well, 50 times 2 equals 100, right? 50 cents plus 50 cents is $1. Okay, so if we're going to multiply by 2 here, then we have to multiply by 2 on the top also. That means that our P2 is going to equal 100 times 2. That's 200. We're still going to use millimeters of mercury. So that's our answer for number 1. Number 2. Here we have a word problem, but we're still going to do the same thing using our pressure and temperature equation, identifying our numbers that are given, and then solving for what's missing. So we read the problem. At 273 Kelvin, okay, so that's temperature 1, we can put T1, the pressure of a sample of nitrogen is 1,000 atmospheres. ATM stands for atmospheres, so that's P1. What will the temperature be at 250 atmospheres? 250 atmospheres is our P2. And this says, what will the temperature be? So this is our T2, and it's our unknown. So let's go ahead and make our proportion. So we have that 273K over 1,000 atmospheres equals 250. Oh my goodness, I just made a mistake. This is why you can't just follow the sentence when you're setting up your variables. If you notice, I put temperature on the top in my fraction where pressure should be on the top. So we're going to go ahead, erase these, and switch them around. Okay, so really important to check what you're doing as you go. Okay, so 1,000 ATM on the top, 273K on the bottom. This was 250 atmospheres. That was in the right place. And we're solving for K. That's our T2. And again, you can use whatever variable you want. Okay, so here we can do this two ways. We could cross multiply and then divide to get our T2 by itself. That's the slow way. So I want to do the fast way again by just identifying the relationship between our P1 and T1 and the P2 and T2. We can figure it out based on pressure, the relationship between pressure 1 and pressure 2. So here, pressure 1 is 1,000. Pressure 2 is 250. We want to know what's the factor here that changes them. In this case, 1,000 is bigger. So it's 1,000 divided by what equals 250. Well, I can think about this the other direction too. I can think 250 times what equals 1,000. Either way, I can figure out that the answer is 4 because 250 plus 250 is 500. Add another 250 plus 250 for another 500. That's going to get me 1,000. 500 plus 500 is 1,000. So that means that my factor here in the middle is 4. So in fact, to go from 1,000 to 250, you divide by 4. So you can get rid of that right there. Let's put a 4 right here. Great. So that means we're going to do the same thing on the bottom. 273 divided by 4 equals, and I'm not going to do that one in my head. I'm going to grab my calculator. 273 divided by 4 is 68.25. 68.25. Remember, our units are Kelvin on temperature. So there's our answer. 68.25 Kelvin. Next problem. At 500 K, so that's our T1, a 5-liter sample, liters, well that's volume, of oxygen has a pressure of 760 torr. Okay, that's P1. If the temperature doubles, what will the new pressure be? If the temperature doubles. Okay, so this is telling us what happened to the temperature, but it doesn't give us a specific value. Let's go ahead and fill in what we have, and then we'll figure out what this question is asking. So we're given P1 and T1 for sure. Remember, torr is a unit of pressure. So 760 torr. So that's P1. 500 K, that's Kelvin. T1 equals, okay, do we have a P2? No. It says, what will the new pressure be? So that's got to be our P2, the unknown. Okay, the temperature doubles. Well, we can figure that out. Temperature doubles. 500 Kelvin times 2. Well, that's 1,000. Right? 500 plus 500, or 500 times 2, 1,000. So we actually have our T2. It's 1,000, so we'll put it right here. And then we're solving for pressure 2. Great. So if we already know our relationship here because we had to figure out the relationship between our temperature 1 and temperature 2 to find temperature 2. So our relationship between our two fractions is times 2. So we just do that on the top also, in the numerator. So we're going to do 760 times 2 to get our new pressure. 760 plus 760 is 1,520. So that's going to be our P2, 1,520. So that's P2. And we need our units. Our units for pressure are torr. Notice here that we can use any pressure units, but we need to keep our temperature in Kelvin. Great, so that's our answer, 1,520 torr. Okay, now we have one little extra concept called standard temperature and pressure. So anytime you see STP, it's going to stand for standard temperature and pressure. And all it means is 0 degrees Celsius and 1 atmosphere. You just have to remember it. It doesn't change. It's telling you that data was taken or an experiment was done under these specific conditions, 0 degrees Celsius and 1 atmosphere. That also means 273 K and 760 torr or 760 millimeters of mercury. So that's just something we need to remember. Come up with a way to remember it, please. Have a great day.